This is a potential energy curve for covalent compounds. And so if we look on the x-axis, this is internuclear distance. So what that means is the distance between one nucleus or the two different nuclei within the same bond. And this is measured in picometers. On the y-axis, we have potential energy, and this is measured in kilojoules per mole. If your energy, potential energy here, is greater than 0, what that indicates is that we have an unstable atom arrangement. If it is less than 0, then that indicates that this is a stable arrangement. And we're going to talk about is the bond formation for hydrogen. And so right now I have 2 hydrogen atoms and they are far apart, which means there are no attractive or repulsive forces, and the potential energy is going to equal 0. As the hydrogens get closer together, there are going to be some of both types of forces, and you can see that the potential energy is decreasing, indicating that this is a more stable arrangement. And then when we get down here, notice that we have the lowest potential energy, and now we've reached a balance between these attractive and repulsive forces, and this is a stable arrangement. So let's talk about what happens when the atoms are at this point. So the first thing is the bond energy. If I look on the y-axis, this represents then the energy required to break the bond. Now, if you're already familiar with bond energy, you know that bond energy is an endothermic process. And so this value should be positive because to break a bond requires energy. And so how can this energy be negative? And that's because remember that this diagram is about bond formation. And so the bond energy would be the same value, but it would just have the opposite sign. If I look on the x-axis now, this is then the distance, and so this represents the bond length between my 2 hydrogens. If the hydrogen atoms come even closer together, then what happens is now the atoms start to feel strong repulsive forces between them. The potential energy is now greater than 0, and this would be an unstable arrangement. So what I have here is a potential energy diagram for an XY single bond. And you can see where the bond energy is for this bond and the bond length is for this particular bond. And if we compare this then to an XY double bond, which is the red curve, now notice that the bond energy is significantly greater and the bond length has now shortened. And that's because now there are more electrons being shared that's resulting in this stronger bond. Next, you're given a potential energy curve for a carbon-oxygen triple bond, and a student claims that the carbon-oxygen single bond will be less deep and shifted to the right compared to the triple bond. And so this question then asks again to do 2 things. The first is to state, do you agree or disagree, and to explain why or why not. So please stop the video, answer the question, and then press play when you're ready to continue. You can see here that the red curve is the carbon-oxygen single bond. It is less deep. And then if we look at the lowest part of the curve where that matches on the x-axis, that would represent the bond length. And you can see that the single bond then is longer than the triple bond that we have here.